The Hellgate Bridge is a vital part of the New York and United States coastal railway network. It facilitates the transportation of goods and passengers through railroads, connecting New York City with the north and east of the country. Construction of the bridge began in 1912. It was designed by Gustav Lindenthal and its construction was supervised by civil engineer Ralph Modzelewski. Construction of the bridge was a significant challenge due to the strong currents and complex geology of Hellgate Strait. The demolition of several rocky islets and the excavation of large quantities of rocks were necessary. The Hellgate Bridge was completed in 1919 and railway traffic was officially opened in March of this year. The main purpose of the bridge is to provide a railway line for the transportation of cargo and passengers. The bridge crosses Hellgate Strait, which is a part of the East River connected to the boroughs of Manhattan and Queens in New York City. The main arch of the bridge has a distance between the towers, approximately 301 meters. This makes it one of the longest suspension bridges in the United States. The towers have a height of approximately 103 meters from the base to the top of the towers. The height of the bridge over Hellgate Strait and the East River is approximately 56 meters. In order to correctly carry out the finite element analysis of the entire arch, a sketch was made in Inventor, which shows that there are 68 nodes, 133 sections and 53 different angles. A train of this type weighs about 92 tons. Just the locomotive and a carriage weighs about 15 tons without load. Estimating that a train can pull up to 50 freight cars, then its total load would be 2,092 tons. The locomotive measures around 18 meters and each car is around 15 meters. Depending on the length of the bridge, it fits in a train of 21 cars plus the locomotive with a total length of 318 meters. Therefore, the total weight would be 932 tons. Since there are 3 railways, 3 trains can pass, therefore we multiply by 3, which would give us 1,864 tons. The total strength would be 18,285 meganewtons, which is applied at the centroid of the train, which is 169 meters. In the boundary conditions we have that the bridge on both sides is restricted by an embedment at the top, as well as at the bottom. The material is a structural steel which is isotropic and its elasticity is 210 gigapascals. This material was chosen for its strength, durability and ability to withstand heavy loads. It is evident that there are 33 lengths for the middle sections of the bridge. The bridge is symmetrical, so the other half is exactly the same. However, being symmetrical, the other lengths will be exactly the same, having a total of 33 different lengths. And from ANSYS. For this we are going to analyze 3 areas in ANSYS that are 1 square meter, 1 meter on each side. The second area is 2.25 square meters, 1.5 meters on each side, and the third is 4 square meters, that is, 2 meters on each side. In the analysis directly from ANSYS with the first area of a square meter we find that it has a deformation of -1.5921 on the y-axis. About our origin. This where at node 61. Since this is where we directly apply the load as it is a point load of 6,095,280 newtons. It generates that noticeable deformation that we can find. All the deformation occurs at nodes 59 to 63, as well as in the nodes and elements associated with them, both in the upper part, which is the structure itself, and in the part of the bridge, which is the completely horizontal. We find that with the area smaller than 1 square meter the deformation is -1.5921 meters. As I had mentioned, regarding our origin in area 2, node 61, which is where the load is applied, has a much smaller deformation and node 3 much smaller. These values are -66.849 times 10 to the -3 meters and the area 3 of 4 square meters. The deformation is 3.98 by 10 to the -3 square meters. These negative values directly for the Scilab analysis we find that we have 38 nodes. This gives us to understand that we have an overall of 76 times 76 and an overall F of 76 times 1. That's because there are 38 nodes, because we are going to apply only half of the bridge and then apply it by symmetry. This gives us to understand that we have 73 different elements, 29 angles. Most of them are not repeated, and with the load, the module and the area of a square meter, we have that each element has its global k, 73 local k, and then add all these local k and their positions to the global k with each nodal position x, and this then to extract the global k with the boundary conditions and apply and find the displacements in the conclusions section for the analysis directly. So we have to think that it would be much better to analyze a distributed load along the bridge instead of a punctual load or applied to a node. This is so that the bridge does not have so much deformation, and we can study a little better what happens in each node and in each element, not only in the straight part, which is the bridge where the trains pass, but in the entire curved part that it is the structure. Now in the Scilab part of Scilab, it is important to take into account the direction of the elements with respect to the nodes, since with the inverse and the boundary conditions it gives us a singular matrix, as well as understanding the use of symmetry in the program.